Okay, so we cannot use the language A suffix TM as an example of a language that is not even Turing recognizable, okay? Because it is Turing recognizable. We actually proved that earlier, page 176 in your text. That's a few pages back from where we are at the moment. Okay. All right. Now, before we do move on to find a language that is not even Turing recognizable, and let alone undecidable, we've spent three sessions showing that A suffix TM is undecidable. So in this final session we'll try to, I'll give you an example of a language that is not even Turing recognizable. But ATM is not that language because it is Turing recognizable. Right? Now to find this language, this new language that is not even Turing recognizable, we need an intermediate step. We need to go into in fact the theorem. But basically, the basic idea is a bit of revision. The complement of a language, what is that? Well, it's the set of all strings. So let's say you have a language A, and the complement of that language, let's just call it AComp, short for complement of. Okay. So AComp is the set of all strings that are not members of A. Okay? They're all the other strings that are not members of A. So a bit of revision. Okay, now, and here's, it's just a lead-in, and we'll get a formal statement of the theorem soon. But we're heading towards another theorem. And that is, if a language and its complement, if both of them are Turing recognizable, then the language itself, A, is decidable. Maybe that seems intuitively obvious to you now. Hopefully you've picked up enough experience with dealing with this kind of stuff. Hopefully you're getting a sort of feel for it. You can start to feel it intuitively, that might seem fairly obvious. If the language and its complement, if both of them are Turing recognizable, then the language is decidable. Okay? Right? Okay, so let's turn that result on its head, twist it, and work the other way. So that implies, therefore, so for any undecidable language, then either the language itself or its complement must be Turing unrecognizable, or is not Turing recognizable. Now, this is me here. This is not Sipser. I'm just trying to spell that out a bit more. So, this language L is decidable. Here's the statement of the theorem, in a sense, in symbolic logic form, somewhat. So the language is decidable if the language is Turing recognizable and the complement of the language, LC, is Turing recognizable. So if both of those are true, the AND here, then this language is decidable. Right? Well, if it's not decidable, so not D for decidable, so if this language is not decidable, that implies either the language is not Turing recognizable or the complement is not Turing recognizable. Yeah, I've written this out sort of to make it seem a bit clearer in symbolic logic form. Yeah, this is just symbolically saying what this is saying. All right. Well, we know what the complement of the language is. We've done that. Okay. Now here's a new definition, new term. Co-Turing recognizable. What does that mean? Well, it's about a language. It's a label you apply to a language. So we define a language is so like with co-Turing recognizable if its complement, L of C, if it's here it tends to get. I think Sipser writes it as a bar. Let me just check. Yeah, a bar. Oh, I'm jumping ahead a bit here. A bar. So I've put C for complement. He just puts a bar over the language. So language A, so the complement would be A with a bar over it, the horizontal line over the letter. Okay. Okay. So a language is said to be defined to be co-Turing recognizable if its complement, the complement of that language, is Turing recognizable. Okay, so, memorize that because we're going to use it. Okay, now here's the actual formal statement of the theorem from here. So theorem 4.22, 22nd thing. Oh, by the way, I think figure 4.18 is missing in the text, just an error. I had to reinterpret things. The editing of the text is not perfect. There's a missing figure. Well, the figure's there, but it's the figure number, like it skips one, like 4.18, just gone. It just got eliminated. So he goes from 4.17 to 4.19, I guess. Right? Okay. So here's the theorem statement. So strictly speaking, it should be 2.1, 4.2.21, but it doesn't matter. It's just a label. Okay. So a language is decidable if and only if. So it's a if and only if type proof. Right? Two ways, left to right, right to left. A language is decidable if and only if it's Turing recognizable and co-Turing recognizable. Okay, so we're using this definition here. Rewording that, a language is decidable if let's see, what is it? If the language is Turing recognizable and its complement is Turing recognizable. It's just using the definition of co-Turing recognizable. Okay, that is, a language is decidable when both it, the language, and its complement sorry, I've left out a little bit. And its complement is Turing recognizable. Okay. All right. Now, as usual, this is me rather than Sipser. I encircle the left-hand side, label that mathematical statement P, encircle the right-hand side of the if and only if statement, and label that mathematical statement Q. And then I talk about P if Q and P only if Q. And I present it in the math style. I think Sipser's rule of thumb is that his rule of the order, which do you present first, the if case or the only if case? I think his rule is that he presents the easier proof first. And so that sometimes means from left to right, sometimes means right to left. But I'm sticking to the math convention, which is that you start the if case. You do the if case first. Okay. So So I'm trying to get you guys to be math guys rather than computer guys, to follow the strong convention of mathematics. So if case first. So in other words, P if Q. And what is P? This mathematical statement P. A language is decidable. Well, yeah, a language is decidable. A language L is decidable. Okay. And statement Q is that language is Turing recognizable and co-Turing recognizable. So that's mathematical statement Q. So P if Q, in other words, if Q is true, then P. So Q arrow P. And Q is the right-hand side. So in other words, you start with the right-hand side, prove the left-hand side. Yeah, we've been through this many times before, so you are probably very familiar with this by now. Okay. Alright, so we're starting with the right-hand side. And the right-hand side is the language is Turing recognizable and co-Turing recognizable. So in other words, let the language be A. So language A and A complement is, you know, A bar, okay, complement of the language. So in other words, both A and A bar are Turing recognizable. And that means that A will have a Turing machine called M1 that is a recognizer for that language A. Remember, well, don't need to go through it, I've done it many times. A Turing machine recognizes a language if it accepts all the strings of the language, and that's it. Nothing further in the definition. Okay, and there'll be a second Turing machine called M2 that recognizes this language, the complement A bar. All right. Now we can take these two machines